Good afternoon. Today we will explain a few things about the stress tensor that we have introduced at the last lesson. So we could recall that the second Newton's law of motion tells us that the rate of change of the momentum of a system computed on a material volume is equal to the resultant of forces applied to the body. Now we can separate the resultant of forces into volume forces plus surface forces, and the surface forces being the resultant of the actions of the loads that are applied to the system through its boundary. So this would be the surface, the boundary, the material surface of our system, and through the contact with the outside environment, a resultant of forces would be generated. Now let's see more in detail how this force is generated. Well, we have here some infinitesimal surface, which we can call ds, and this infinitesimal surface would be responsible for some infinitesimal surface forces. So let's pretend it is something like this: infinitesimal surface force. And once we separate the various contribution and sum up the various vectors, we obtain this surface force. Now the question is how this infinitesimal surface force is generated, and here we must be a bit more specific, because we have some infinitesimal surface. So this would be another infinitesimal external surface, and we see that each infinitesimal external surface has an outward normal, and this outward normal of course depends on the position. So it would be this one here, it would be this one here, and so on. Now the outward normal points, whatever it happens to be, and the infinitesimal force would be also distributed with some form in space, which we don't know in advance. Now what we know for sure is that the actions on a surface can be parameterized by the vector of local tensions, and these tensions can be written as T, and this is a local vector. Now last time we have seen that depending on how the normal is oriented and how the local loads exert an action on the surface, the outside tension vector can be positioned in different ways, can point at different directions. So the question is how do we relate this tension vector to the infinitesimal force, or how do we relate this tension vector to this force? So something we have put forward last time is that this force vector is written in this way: integral over S, being S the outward, the material surface, of a tensor dot n ds. Now ds is the infinitesimal surface, n is the outward normal. What we miss is the relation between this tensor that we have justified but not really proved to the local tension vector. So how do we prove that this is indeed a tensor? The tensor is the only quantity that has the right to stay there. So let's consider this tension vector as a force per unit surface. So it is not a stress, it is indeed a vector, because a stress would be a tensor. So this is a vector, but it has the dimensions of Newton per square meter in the international system. So we might write, for example, that dFs, so the local infinitesimal force, is nothing but the local tension times ds. Okay? So this would give a force. Let's hope I'm correct. Okay. So something now I would like to show is that this tension is in fact T dot n, and this T is the tensor we were claiming last time. Okay, so something we can do is to sketch a very classical drawing, which is the Cauchy tetrahedron. So we have a Cartesian reference frame, these are the axes, and now I can have a solid made in the following way. So I have here one triangle in the xz plane, so that this edge is dx, and this edge is dz. Now I sketch another triangle in the yz plane, and clearly this edge would be dy, and then by necessity I close the sketch by having a third triangle in the xy plane, and then you might think of the inclined surface, and this inclined surface we call ds. Okay, so let me so this would be ds, and by ds I mean this inclined surface. Now this surface will have some outward normal, and this outward normal I'm trying to draw it in a quite general way. This would be our outward normal. Okay, what about the outward normals of the other faces? Now, of course, for this triangular face in the xy plane, the outward normal would be this one. But now, this would be anti-parallel to z, so we can call this normal minus z hat. So minus z hat would be the opposite of the z versor. And then we can apply the same argument to the other faces. So in this face in the xz plane, the outward normal would be this one. No, sorry. It would be this one. So from here it would be something like this. this would be minus y hat. So minus y hat. And finally here, so let's pretend what is this one? This would be n, and here we will have something anti-parallel to the x-axis. And this would be minus x hat. Okay, so why do we need this complex arrangement of normals? Because something we should keep in mind is the following observation. Now, let's focus on this surface. Now, this surface will have, I need another color, will have this tension vector, and it will have this outward normal. Okay, now this is just because I'm considering for my particular problem that this is the volume, the material volume, and this is the outside. So this would be the outward normal, and this would be the tension. Now, the force at a point is whatever it is, regardless of the reference frame we are using or regardless of the assumptions we are doing. So something we could conceive is that we have another problem in which our material volume is everything outside, so it would be something like d prime, and then at this point the outward normal will not be this one, but will be, let's see what I can use, let's use this one. This would be the outward normal. Now, if this is n, this is simply minus n. Now, the tension at this point must be exactly the same, because this is the status of the tensions at one point. So the forces per unit area applied at one point of a continuum medium. So whether I look from one side or from the other, it doesn't make much difference. So think of this sheet of paper as our surface. Now, if I imagine that my volume is here, the outward normal will point at this direction. If I instead change my mind and I think that the volume is this one, then the outward normal will point in this other direction. But the tension vector, assuming that it is, let's see if you can see it. Well, assuming that it is this pen, it must be this one, either if the normal points here or if it points at the opposite direction. So this observation allows me to claim that the tension vector is a function of the normal, but it is such that the tension vector at the same point but for an opposite normal must be related to the other one in this way. And this is a very important observation. So the tension must be an odd function of the outward normal. If you like, this is nothing but the third Newton's law of motion. For every action, we have an opposite and equal reaction. Okay, now we can make some claims for our tetrahedron, because now we have an object, a volume of fluid, which we imagine to be enclosed in this tetrahedron, and this is subject to some surface forces. Now, what are these surface forces? Well, first of all, let's look. I can fit all the derivations into this small blackboard. So actually what I would like to do now is to write F equal ma for this tetrahedron. So what is the mass? The mass for this tetrahedron is the volume, and the volume is dx, dy, dz, times the density of the fluid, and then ma would be, I can write here, ma would be dx, dy, dz, and this is the infinitesimal volume, times the density of the fluid, times the acceleration. Okay, so this would be ma. Now, ma is equal to F. F in turn is the volume forces plus surface forces. So let's see what are the volume forces. Well, the volume forces are just the density times the volume of the fluid times a vector of infinitesimal forces. So we can write here the density times the volume, dx, dy, dz, times the specific volume forces. Okay, so just for you, this is ma, this part, this is fb. Now we miss fs, the resultant of the surface forces. So let's write one at a time. So of course we have here on this inclined surface, we know we have some tension, and this tension vector would be a function of the outward normal. So this would be tension vector as a function of the outward normal times ds, and ds is this infinitesimal surface. So we can call it ds. So I have written before that T and ds is df. Of course, this is just one of the 4 surface contributions, because then we have one contribution on the surface element on the xy plane, one on the yz plane, and one on the xz plane. So what would be the contribution for the xy plane? Well, first of all, we have the tension, and this would be tension as a function of the outward normal. So we can write plus the tension of minus z hat times ds. Now ds would be dx dy divided by 2, because this is a triangular surface. So dx dy divided by 2 plus, now we have 2 additional contributions, and they would be the contribution from the xz surface and the contribution from the yz surface. Now I will write the contributions over. So for the yz contributions we have t vector, the outward normal would be minus x hat, and the surface would be dy dz divided by 2. So dy dz divided by 2 plus the final contribution, that would be t vector of minus y hat dx dz divided by 2. dx dz divided by 2. So this is a tetrahedron. So there are 4 surfaces, and then we have 1, 2, 3, 4 contributions, and all of them account for Fs. The volume force and then the acceleration. Okay, now as is, it looks a little bit messy, but we can try to simplify it. So first of all, something we can notice immediately is that here we have a volume, the density, and then we have area and force. So something we can do is to lump the factors together. So I can take this part and just lump here by writing A minus F, so that I make some room over here. Now, let's take one of the terms. So for example, this one. This would be t minus x. So let's focus on this one only. So this would be t minus x, but we know that the tension is an odd function of the outward normal. So we know that t minus x hat we can write as a minus t x hat. And this is something we have learned before. Now, this dy dz divided by 2 is this area. Let's see if I can make it evident. So it is the area of this triangular element in the y-z direction. Now, if we think of a tetrahedron, this orange shaded area can be thought of as the projection on the y-z plane of the inclined surface. So I can write, let me write it here. So the orange shaded area, so the y dz divided by 2, and this is the area which I have shaded with the orange chalk, is the projection of the inclined area on the y-z plane. So the inclined surface is ds, and in order to project it, I have to see what component of the outward normal points in the x versor. So it would be n dot x versor. And now, since the scalar product is symmetric, I can write this as x dot n. Okay? So, in place of dy dz divided by 2, I can write ds x hat dot n. So, ds x hat dot n. Now, I don't have to convince you that I could do the same for the second term and for the third term. So I'm just writing minus t y hat ds, and by analogy this would be y hat dot n, and the final term, which is this one, I can write let me write it here, minus t vector z hat ds z hat dot n. Okay? Now, 1, 2, and 3 I can write together. So let me take them out. from here. Okay, so how can I write them? Look, I have ds, which is common to all three terms, dot n, a scalar product with a normal, which is common, and then minus, which is also common. So I can write minus square bracket t x hat x hat plus t y hat y hat plus t z hat z hat. Now close dot n ds. Okay, so this is MA equal to MA minus volume force equal to surface force. Now look here, this is the infinitesimal volume, dx, dy. Actually, it is not true. Sorry, I did it wrong. It is dx, dy, dz would be the volume of a parallelepiped. It's not of the tetrahedron. So let's call it a dv, just to be more correct. So this is dv. Okay. Now, what I can do is to write the infinitesimal volume as the infinitesimal surface. Maybe I can write it here. Well, this will be used. So the infinitesimal volume, dV, would be the infinitesimal surface times the infinitesimal height of this tetrahedron divided by 3. Now, actually the infinitesimal height would be some length pointing into the tetrahedron, but I don't want to make even more messy this sketch, and so I can replace the infinitesimal volume by the infinitesimal surface times the infinitesimal height divided by 3. Okay, and now I should recall the initial question. So the initial question is how the tension vector at one point looks like. Now, if I look at this sketch, I can ask myself, am I balancing tension vectors at the same point here? Well, the answer is no, because Tn is at this point. T y hat is instead at this point. Now, this point and this point are close, but they are not exactly at the same point. So what I can do is to make a limit in which I shrink this tetrahedron while keeping similar its shape. So this is an affine transformation, so that all this centroid will collapse to the same point. Now, and this might clarify my effort to transform several terms, ds can be cancelled out from these three terms. So as you can see, this limit process doesn't affect this term. Sorry, this should be cancelled out, of course. Doesn't affect this term as well, because here there is no trace of what is left, but the limit still affects this term, because as you can see, even if I cancel out ds, I still have dh divided by 3. Okay, so when I take the limit for the size, the edges of this tetrahedron approaching 0, the right hand side of this expression cancels out. Okay, this is just a consequence of the fact that the volume forces tend to 0 faster than surface forces while shrinking the element. So while I take this limit, this goes to 0, and what I'm left with is that Tn minus this expression is equal to 0, which I can write in this form. So I can write as Tn equal, so now this expression I can bring to the right hand side, and so I will have T x hat plus T y hat plus, let me make some room, T z hat dot n. And this is exactly what I need. So this tells me that the state of tension at one point is given by this expression dot n. And this expression is exactly the tensor I was looking for. So this is the expression of a second order tensor, and now I have proved that indeed what I need here, actually this Fs that I could have written in this way, T n ds, in fact Tn is this one, and this second order tensor is made in this way. So actually the state of tension at one point, and keep in mind that now it is indeed at one point because we have shrunk the tetrahedron at the origin, the state of tension at one point along one specific directions can be built from the state of tension along 3 orthogonal directions through this expression, and this expression is that of a second order tensor. Now this is a proof due to Cauchy, and now we can feel relieved that it is not just plausible that the state of a tension must be described by a tensor, but it is the only possibility. Now we can say a bit more about how this tensor looks like, because actually something we could do is to write this tensor in this way. So this would be the tension along the x direction and then projected along x. So this could be written like txx, txy, txz, and then the other terms, tyx, tyy, tyz, and tzx, tzy, tzz. So now we might ask, is this second order tensor a general one, or can we claim it has some specific properties? So now the idea would be the following. Now think of a parallelepiped, and just to make our life easier, let me use another color. We can identify one rectangular section of this three-dimensional object. This is x, this is y, and then our section will have, say, an edge of length dy. So dy would be this length, and another edge of length dx, which would be this one. Good. Now, since we have this tensor, the tensor made in this way, then what we can do is to compute here, actually to sketch here the various elements. So txx would be this one. So txx. So why the double index? Because it is the force per unit area applied along the x direction to a surface whose normal is directed also to x. So accordingly, this would be txy, because this is a force in the y direction but applied to a surface whose normal points in the x direction. And now we can do the same here. So this would be tyy, while this one would be tyx, because the force points at the x direction, but it is applied to a surface whose normal points to the y direction. Well, of course, we could have here similar forces. So like this, and then like this, and like this. Good. Now, let's make the balance of rotation. So the easiest is to choose the origin, and so we can write the balance of angular momentum. So the rate of change of the angular momentum is equal to the resultant of the external momenta of the forces applied to the body. So this is quite easy, because all the world normal loads will have zero momentum, because the harm of each force is zero. Instead, we can make a little bit in detail this moment. So txy will be applied to a surface which is dx, and let's pretend we have dz in the direction orthogonal to the blackboard, dx dz. And then what is the harm of this force? It is just dy divided by 2. So dy divided by 2. Now, this is one moment. So, see, yes, one moment for this force. And what about this one? So, if this is positive, since it is counterclockwise, this tyx will generate a clockwise, so it will be a negative moment. So we have tyx. Now this is applied to a surface which is dy dz. So dy dz, this is a subscript, so yx. And now the harm would be just half of this h, so the x divided by 2. Okay, so this one would be actually the same as this. Here there is the normal pointing at the opposite direction, so we can write a 2 here, a 2 here, and we have summed up also these contributions. And this is the momenta of the external loads, and now this would be equal to what? To the moment of inertia of this object, and this would be something like the mass, so the density times the volume times the radius of gyration, which for a parallelepiped can be computed very easily. Anyway, the important point is that since the edges are all infinitesimal, this is the volume, or the surface times the harm, is a cubic power of the infinitesimal lengths, while here we will have something at the 5th power of the infinitesimal length. So it will be the volume, so dx, dy, dz, times the density, times some squared gyration radius, which would be some infinitesimal radius. So let's call it dr squared. So this is the gyration radius, omega dot. And this is the rate of change of angular rotation. Now again, the same as before, we want to know how the different elements of this tensor at the same point are related, and we are not answering the same question because tyx is here and txy is here. So what we need to do is to shrink this parallelepiped at the origin while keeping the shape constant. So as we can see, now the two factors can be cancelled out. Dx, dy, dz is common to all the terms, but here we have the radius of gyration that goes to 0. So a pointwise object has a 0 moment of inertia. So these terms collapse to 0, and all we are left with is this relation equal to 0. And this gives txy equal tyx. So you see, there is a minus here. When we bring to the right hand side, it will give txy equal tyx. And since x and y are not special directions, they can be everything. So at least I can take this set of axes and tilt in every possible direction. This implies that here this would not be tyx, it would be txy. I just derived here xy, but similarly this is txz, and this would be txz as well, and the same here, xy, and this would be this yz, and this would be yz. So this is t. We have proved using the balance of angular momentum that not only this is a tensor, but this tensor must be symmetric, which is very good news because it implies that rather than having 9 independent quantities, we have just 6. Okay, finally, a final specification is how this tensor looks like for a fluid at rest. So we know that by definition a fluid develops shear stresses whenever there is a rate of change of angular deformation. So in order to for a fluid to manifest itself, you should shear it, you must deform. So you should start from a fluid element like this, you apply a tangential stress, and then you should see an element that keeps deforming continuously in time. And in this case, we know that if this is the angular deformation, we have this relation that tau is equal to mu, the dynamic viscosity, times gamma dot, and this is tau is the tangential shear stress. Now, which is of course a surface load, so it must be part of this tensor. However, what can we say if the fluid is at rest? So now we have this fluid element, and we do not apply any tangential stress. Well, the only action that the fluid can exert is pressure. Actually, without deformation, a fluid element can only withstand a pressure load, and the pressure load, if this is the outward normal, is oppositely oriented. So this would be a pressure force. Now, since this is the outward normal, n, this force must be, by necessity, minus p, n, being n the outward normal, and then we have the area of the wet surface, and so we can call it S. Now, also this component must be part of this tensor. Now, how can we relate the tensor in this configuration? Keep in mind, always at a point. So here we will have a pressure here, a pressure here, a pressure here, a pressure here. Now, fortunately, someone has already solved this problem, because this is the Pascal principle. So what we need to do is to make the balance, the equilibrium of this element about some point, shrink the element to 0, and the final solution would be that the tensor T must be given in this form, minus P I. Why is it like this? Well, if I just plug this definition into this integral, what I get is that integral over S, now in place of T I would put minus P I, the identity tensor, dot n ds. But I dot n, by definition, the identity tensor maps any vector in itself. So I dot n is n itself, and so this integral would be minus integral over S P n ds, which is just the way we compute general pressure forces. Okay, so this is the component of T due to pressure, so in absence of any angular deformation. But of course, this must contain also the part due to the angular deformation. So generally, we can write that the tensor T is made of two parts. This part, that is the one due to pressure, which is the hydrostatic part, plus another component, which is called the deviatoric part, and this part is the one due to the deformation of the fluid element. So, at the end, what we can do is to write that the surface forces can be written in this way. Can be written as minus integral over S P n ds which is this part already projected around the normal, plus integral over s tau, and this is the deviatoric part, dot n ds. Now you might wonder how this tau looks like. Keep in mind that this is the part which originates from the deformation of the fluid element. So in order for a fluid element to deform, there must be velocities inside. So if u is the velocity field, we can call E the symmetric part of the velocity gradient tensor, and then it can be shown that for a Newtonian fluid, so an homogeneous isotropic medium, tau has this form, twice mu E minus 2/3 mu divergence of u times I. Now this is the constitutive relation for Newtonian fluids, and it can be proved starting from basic principles, but it takes some time, so we will devote a lesson per se just to prove that tau, the deviatoric part of the surface stress tensor, has indeed this form for a Newtonian fluid. Okay, thank you.